Okay, there are two open source implementation, 3.1 and 3.2 on Checksum and CRC respectively. And the Checksum implementation is in software, and the CRC implementation is in hardware, in Verilog. And the code shown for Checksum is drawn from an RFC. In RFC 1071, okay, that's a C code. But it's not used, again, it's not used in the link layer. The link layer does not use Checksum. Okay, they use CRC. Okay, we put it here just to show how it could be implemented, but actually it's not in use in the link layer. And the code is drawn from one RFC. And the checksum code really used in the IP layer and or the transport layer, it's in assembly code, not in the C code. Okay, and you will see that, well, the assembly code version of checksum in chapter 4. So we will see that in chapter 4, but not in this chapter. In this chapter, it shows the example code drawn from an RFC. Okay, but the architecture, the idea is the same, that for checksum, you have the word coming in, and then do the addition together. So the first come in, and then stay here for the second word, come and circulate back, and the second word come in, add up together. So these two will be added together, and then the result will circulate back to add with the new word, the next word. So by combining these two streams together, you would get the sum back, and then at the end you output the checksum value. Okay, and here because some CPU right now has 32-bit word. If the CPU word is 32-bit, and your checksum field is only 16-bit wide, what happened is that you do the addition, and each word is 32-bit wide, but at the end you need to fold. You need to fold the 32-bit into 16-bit so that you can fit into the 16-bit checksum field. Okay, so that's the checksum. As for CRC, it's again circulate that it's initially you do the exclusive OR, internal it's exclusive OR, that you would input the data and then do the exclusive OR repeatedly. And this is the initial pattern, that the pattern you input, and then the data come in here, and then you do the exclusive OR, and then you loop back, and then to do the exclusive OR again. So at the end, you end up the result. So you do the exclusive OR shift, exclusive OR shift, exclusive OR shift, and then you got a result. And in these two open source implementation, we shown the C code drawn from an RFC. And here we don't show the actual Verilog code, but it's there in a .v file, because it's Verilog program. Okay, the next issue will be the error control. that what happens if you do the CRC and it's incorrect? If it's correct, fine. If it's correct, should I acknowledge the sender? If it's incorrect, should I send a negative acknowledgement to the sender? Okay. So if I do CRC, I have error, or I have correct result. What happened? So if there's an error, then what I can just silently discard. Okay, this frame. Okay, if it's correct, I might send a positive acknowledgement, or I might send a negative acknowledgement. And it shows that the Ethernet does this. Okay, if it's incorrect, the CRC result is incorrect, I just discard. I don't send a nec or ec. Nec is negative acknowledgement, and ec is positive acknowledgement. So I either correct or incorrect. I just don't respond. Okay, if correct, then I continue to process. If incorrect, I drop it without sending any frame to the sender. That's Ethernet. And PPP the same. You will see that PPP does the same. It would discard. Okay. However, HDLC would do this. Say PPP was derived from HDLC, as we will see in the original design of HDLC. It does this and this. Positive, I send ec. Negative, I send nec. Okay, but PPP does this, which is similar to simplified. It's simplified HDLC. And Ethernet does this. How about wireless LAN? Wireless LAN does this. If it's an error, I don't respond anything. But if it's correct, I send an ec. So as you will see that in wireless LAN, it will send an ec to the sender if it received the frame and the frame is correct. Correct means that CRC calculation shows it's correct. The frame is intact, meaning correct. Then the wireless LAN receiver will send an ec. But if it's in error, then I don't send an ec. So if I don't send an ec, the sender would assume that the frame is in error, either lost or in error. So the transmitter will retransmit the frame again. So that's what happened in wireless LAN. But in Ethernet, it does not do this. It does not do ec or nec. So wireless LAN does ec, but does not do nec. Ethernet does not do ec or no nec. Why? Why they make so different choices? The answer could be reviewed later when we see the protocol behavior of Ethernet and wireless LAN. But let me give a quick word. Because Ethernet is reliable, but wireless LAN is not reliable. It's unreliable. So Ethernet is, the chance for Ethernet to have error is very low, but the chance for wireless LAN to have error is very high because the wireless link is vulnerable to errors. Okay. So on Ethernet, when you say a frame is received, no collision. If I transmit a frame and there's no collision, the most likelihood is that the frame is received correctly. So there's no need for nec or ec. As long as no collision, then fine. However, in wireless LAN, the chance for having frame loss or error will be very high. So I need to receive an ec to ensure the frame is successfully transmitted and received. Okay, if I don't receive an egg in a specified time, then I would assume the frame is in error or lost. So I would retransmit. So I rely on an egg from the receiver to make the decision. Okay, so that's the reason why they make different choices. And for PPP, for HDLC, they use this too, but for PPP, it is simplified. Then why PPP simplified the error control compared to HDLC? The same, it would the chance for having error is less for the environment that PPP is used. Okay, compared to the old day when the HDLC was designed. Now the chance for error, and it's used in the wired environment, the wired ADSL, DSL. The chance for DSL to have error is because it's wired environment. The chance of error is lower. So PPP simplified that and says that no need to egg or neck, just do the same thing as Ethernet. Just silent, keep silent. Okay, the next issue is the flow control. It will need to keep the faster transmitter from overwhelming the slow receiver. Okay, and you could use a stop and wait. You transmit one frame, receive an egg, and then transmit the next frame. That's called stop and wait. And who does this? Wireless LAN. You will see wireless LAN does this, stop and wait. So there's no chance for a transmitter overwhelming the receiver in wireless LAN because it does stop and wait. If the receiver does not send back an egg, then the transmitter would not proceed to send the next frame. Okay, sliding window. Well, there's a window size. There's a window size that controlling how many frames can be transmitted at most, or how many frames can be in transit, meaning not acknowledged yet. And who does this? HDLC. HDLC does this. And how about Ethernet? How does Ethernet handle the PPP? How does Ethernet and PPP handles the flow control? The Ethernet says that if there's an error, if the transmitter is sending too fast, if the receiver senses that the transmitter is sending too fast, then it would use back pressure. It means that it would send the carrier signal to keep the channel busy. If the channel is busy, then the transmitter would sense the channel busy and then stop transmission. It would not be able to transmit if the channel is busy. And sometimes the receiver can collide the frame. If the transmitter is sending the frame and the receiver collide the frame, then it would force the transmitter to back off to transmit later. We will see that the collision resolution, you will see that the transmitter would actually back off and try later. So that's in Ethernet, you could use back pressure. However, as we move the Ethernet from broadcast link to point-to-point link, there's no collision anymore. So you would use a specific frame. The receiver would send a specific frame called post frame to stop the transmitter. Okay. So on Ethernet, it would use a back pressure to slow the transmitter down, or implicitly or explicitly send a pulse frame to the transmitter to stop the transmitter from sending more frames. Okay, that's done in Ethernet. And it's done in HDLC, the sliding window. And it's done in wireless LAN. How about PPP? PPP does none of this. Well, in the book, it specifies that PPP has no flow control. No flow control. So that means that it's possible that the sender will send too fast and to overwhelm the receiver. And it says that it's up to the upper layer protocol to resolve this issue. Okay. So from this, you know those popular links, what kind of error control and flow control they use. Okay, we mentioned that HDLC use this sliding window flow control, and the ideal sliding window is this. So if I say the window size is 9 for my flow control, it means at most I can send at most 9 frames outstanding. Outstanding means it's in transit, it's not acknowledged yet. So if I'm sending, if my window size is 9, and I have sent 4 of them already, and the other 5 I could send, but I haven't sent. So I could go ahead to send those 5 frames. And if the acknowledgement for the first 3 frames has returned, then I can move my window size forward. By 3 frames, I can move my window size. Okay. And then now I have more frames to send. So I keep having, and this is a bound, 9 frames outstanding, unacknowledged, in transit. And if I transmit all the 9 frames in the window, then what? I need to wait. I cannot send more. I need to wait for the acknowledgement to come back, so that I can move my window forward. So if all of the frame in the window has been transmitted, I wait for the acknowledgement to come back, so that I can move forward. So that's the sliding window. And this idea is used in HDLC, but not in PPP, not in Ethernet, not in wireless LAN. Okay. However, it's used in TCP. The TCP does window size, sliding window flow control. It does this. But there's a difference. The window size in TCP is dynamic. It's not fixed. In HDLC, the window size is fixed. If it's 8, then it's 8. If it's 16, then it's 16. You can configure that, but it's fixed. However, in TCP, the window size is dynamic, that you can enlarge the window size when the bandwidth is abundant, or you can shrink the window size when the bandwidth is, well, when you detect that there are some loss, then you reduce the window size. So you control this. It's like when you when in a freeway, if the speed of the car, every speed of the cars is slowing down, then you control the entry gate to admit less cars into the freeway. Okay, so you are trying to control the outstanding bit or in transit or outstanding packet in the network. Okay, and that is dynamic. So the window size is dynamic in TCP, but fixed in HDLC. Okay, the final issue, the final two issues, MEC and bridging. It is an arbitration mechanism for the media shared by multiple stations. So it's not just two stations. You need to share. There's competition. So you will see CDM, CSMA-CD, CSMA-CA used in Ethernet and wireless LAN respectively. We'll see that next. And also the MEC sublayer within the link layer need to do encapsulation to encapsulate another header. Okay, so that's a MEC layer. And bridging, as we have said that each link, if it's point-to-point link, then it can accommodate only two hosts or two stations. If it's a broadcast link, then it could accommodate more, probably tens or up to hundreds, but no more than hundreds you can cover by a broadcast link. What if you need to cover more than hundreds or even thousands of stations or hosts? Then you need to extend the coverage by multiple links. So I have a link here, link there, but I need to interconnect those links together. So that means you need to interconnect LANs in order to extend the coverage. And if it's done in the link layer, then it's called bridging. And it's defined in L2.1d. And basically, you need to decide whether or where to forward an incoming frame. And there's a principle which is plug and play or transparent. Perhaps you might not be familiar with the, say, Ethernet switch. So you have Ethernet switch, and each switch have 24 ports, and each port will connect to one station or one host. Okay, and then you have so each switch will be able to interconnect 24 hosts. However, you have so many switches, and you need to interconnect them together. Then it says that you connect the switch together. However, you don't want to spend the effort to configure the switch. You want them to plug and play. You want the switches to plug and play. No configuration needed. Then you need to do the so-called self-learning. So the switch are actually doing, or the bridges are doing self-learning to know who is at which port, or who is from which port. Okay, we'll see that in the final section. I mean not the final, but one of the sections in this chapter. By self-learning is plug and play. Do you if you notice if you have played with some switch and router, you will know that switch are plug and play, transparent. No need to configure, right? You just connect them and they run automatically. No configuration needed. However, if you use routers to interconnect several networks together, then you would find that those routers need to be configured. You need to configure those routers. It's not plug and play. So routing is not transparent. It's not plug and play, but switches are, or bridges are. Sometimes we call switches, Ethernet switch. Sometimes we call bridges. Okay, but they are all the same, and they are transparent. They are plug and play, unlike routers. However, when you do self-learning, there's a possibility that there's a loop in the topology. If there's loop in the topology, then you would have confusion in the self-learning. Sometimes I saw this guy come from this port, but sometimes I saw it come from this port. So I'm confused whether this guy's this interface card, the MAC address, belongs to this port or this port. I might get confused. if there's a loop in the topology. And so the standard say that, okay, in order to resolve the collision, let's enforce a logical spanning tree to eliminate the loop. So they enforce a spanning tree protocol on the interconnected bridges, so that virtually there is no loop. It's a tree, and we know in the tree there's no loop, and if no loop, no confusion in self-learning. And we'll see that again in that section on bridging. Okay, the third open source implementation is on the link layer code graph, the packet flow in the code graph. Okay, so you will see that that's the hardware. This is the hardware, and the driver. If there's an interrupt, hardware interrupt, then CPU is interrupted and pass the control of CPU to the driver, the part of the driver, and this is the function that will get a CPU's control to process the packets, and then call this function to process the received packet. And then at this point, it would need to decide which function to call in the IP layer. Okay, if it's an IP packet inside the payload, inside my frame, within my frame, it's an IP packet, then I call this function. If it's IPv6 packet, I call this. If it's not, and it's an ARP request, then I call this function. Okay, that's incoming. For outgoing, this function in the IP header will call this function in a link layer, and then it will call all the way down here, and this function would then call some other function to program the interface controller, the adapter controller, a chip with a register. So we will program the register on the controller to transmit the frame. I mean, to copy the frame first and then transmit the frame. Okay.